Agreed. Order them iterations of our phase estimation.
Maybe you can turn it off. Use only this one. Okay.
Hello. 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 1, 2, 3. Hello.
Okay? Okay? So, so we have a linear filter like this, which we received two components, X filter desired plus V residual noise. Okay, so if we want to get distortionless response, which means that the output of the filter, we get the same desired signal, you see. So we need to add a constraint that H, the filter, that is applied to the relative transfer function, the steering vector here, will be 1 for all frequencies. And then we assure that X filter desired will be equal to X1. So this is the distortionless constraint for this model. Okay, so what I want to talk before we continue, so we talked about the MVDR. So the MVDR, actually what it tries to do, MVDR, minimum variance distortionless response. So what we try to do is to minimize the variance of the residual noise, which we try to minimize using H for each frequency. We try to minimize the variance of the residual noise, which is H phi V F H subject to the distortionless constraint. And we said that it's also equivalent to minimizing the power of these two. Instead of minimizing the power of the residual noise, the variance of the residual noise, we can minimize the variance of Z, which is equivalent. Okay? So instead of minimizing the variance of the residual noise, we can minimize the variance of Z, which is actually H F phi Y H F, subject to the distortionless constraint. Because under this constraint, minimizing the variance of the output of the estimate is the same as minimizing the variance of the residual noise. Because this is X1. Okay? So if we try to minimize the variance of X1 hat F magnitude squared, so it's equivalent to minimizing the variance of V residual noise magnitude squared. If both are under the distortionless constraint. So if we have the distortionless constraint, both produce the same filter. It's the same. And actually, it's not the same if we have estimates of the coherence matrices of V and Y. But otherwise, these two produce the same filters. But in order to distinguish between them, sometimes we call this minimum variance, minimum power, distortionless response. Okay? Minimum power, distortionless response. So if we know exactly, if we don't have error in this coherence function matrices, if we know this and this accurately, no error, so the filters that we find using the MVDR or MPDR, that's the same. But if we estimate this, then generally they will produce different results. And you can ask which one is better, which one is more robust, and so on. Okay, so there are some works that talk about this, the relation between them and which one produces better results under which condition and so on. Okay, but I just want you to know that there are some differences when these matrices are obtained by estimates. Okay, and then we continue and we talked about LCMV. So for LCMV, linearly constrained minimum variance, what we try to do is to minimize the variance, minimum the variance, which is to find a filter that minimizes the variance, H, subject to not only the distortionless constraint, but additional constraint. So we have some constraint, which we put in a matrix, C. This is the C. This matrix contains the constraint for each frequency, and multiply with F, and this equals to some values, some vector, whatever. We call it, let's call it I vector of constraints, these values. Okay? And we found a solution. Okay? But I don't want to talk about the solution. It's not difficult to find the solution. Well, already we showed what is the solution. But I want you to see the equivalence. Now, instead of minimizing the variance of the residual noise, we can minimize the variance of the estimate. It's the same under these conditions, as long as this constraint, one of them includes the distortionless response constraint. So if in these constraints, one of them includes this constraint, so we can minimize, instead of the variance of the residual noise, the variance of the estimate, of the output of the filter. So we can write it like this. Okay, so the same thing like here, we call it linearly constrained minimum power if you want to identify between them. But sometimes people call this also LCMV, and they call this MVDR. But sometimes people call it MPDR, and this LCMP. But now we understand. Okay, so theoretically it's the same, but in practice it's not the same. Okay, now suppose that we want to implement these problems. You see, suppose that we want to have the same solution of MVDR or MPDR or LCMV or LCMP, okay? Suppose that we want to get a solution, but in a different way. So as you know, when we give different expressions or different derivations for the filter, maybe theoretically it's the same, but in practice it's not the same because of different implementations, different way to derive the filters, different ways to adapt the filters for changing environment and so on. So it's important to derive filters by different methods, okay? So now I will talk about different methods to derive this solution and this solution, okay? These solutions, which is very important because actually many times in practical environments, especially non-stationary time environments, it is more useful, okay? So first, okay, so maybe, okay, so you remember this. I don't need to keep. I can delete it, and if we will need it, I will write it again. But before that, I would like to talk about adaptive filtering, okay? What is adaptive filter? Adaptive filter is when we have a noisy measurement and we have another measurement of noise that correlates with the noise in the measurement, okay? So I will give you an example, okay? So I talk about adaptive filtering. Okay, so suppose that we have a noisy measurement, yt equals to xt plus vt. So this is like the single channel, okay? Single channel noisy environment. But in addition, we have another channel, RT, which correlates with the noise, but it's uncorrelated with the desired signal. So we call it reference channel. So this is a reference channel. Okay, so suppose that we have this problem. What do? Of course, we can ignore this and only try to estimate xt from the noisy measurements, just like we did with the single channel. But if we have another channel such that RT is not uncorrelated with the desired signal, only with the noise, so we can take that into account. What do? We try to find a filter, WT, okay? So what we try to do is we try to obtain an estimate of t, x, of the desired signal. How? So if we knew the noise, what could we do? Okay? So if we knew what is the noise, we could do something like that. We would like to estimate the noise and suppress it from the signal. Okay? So here what we can do, we take yt and subtract. We want to subtract the noise, but we don't know the noise. But what we can do is to find a filter, let's call it WT, such that WT convolved with YT, so this will be, with RT, with RT. So this will be an estimate of the noise. So we would like that this will be an estimate of the noise. So this will give us an estimate of the signal. Okay, of course, we can try to do that. Sometimes if it's not successful, we need to find out why it's not successful. But something like that is called adaptive filtering. Okay? And the thing is, how to find the optimal filter here. So what is the optimal filter? So it turns out that the optimal filter is obtained by minimizing the variance of the measurement, of the output of the adaptive filter. Okay? So this is what we want to achieve. So how do we do that? Suppose that we have a noisy measurement, and we have a reference channel. We can find a filter WT such that Y minus RT convolved with WT will generate an estimate of the desired signal. So we minimize the power at the output, and we can adapt this filter. So this filter, this is the way to write it, like this. So this filter is obtained by minimizing the power at the output. That's why it's very important that RT, the reference channel, is uncorrelated with the desired signal. Because if it's correlated, maybe it will minimize this power, but minimizing the power of the desired signal. But because it's uncorrelated with the desired signal, it means that the only way to minimize the power here is by minimizing the residual noise. Okay? Because the power here, you see, I can prove, the power here, the power at the output, contains the power of two components. One component is the filter desired, and one component is the residual noise. So if we try to minimize the power of this, and the reference is uncorrelated with the desired signal, so it means that the only way to find a filter that will minimize the power here is by minimizing only the residual noise. It will not affect the desired source, the desired signal. Okay? So this is called adaptive filtering. And of course, we can do that similarly in the frequency domain. So I will show. You see, this board is relatively small, so maybe this part. So I will write it here. So we can do that the same. So we can write that YF equals to XF plus VF. And we have our reference channel in the frequency domain. So we have two channels. And then we try to find an estimate, ZF, which is an estimate of XF for each frequency, by taking YF and subtracting a filter, WF, that multiplies RF. And we need to find the optimal W, but by minimizing the variance of ZF. Very nice. So the block diagram is similar. Okay, similar, but instead of T, there will be F. So I don't need to write it again, the block diagram. It's the same, but with frequency. Very nice. So this is like reminder about adaptive filtering. Now suppose that we don't have a reference channel with a noise-only component. So here I assume that with one sensor I measure desired signal plus noise. In the other channel I measure just noise that is correlated with the noise in the measurement. But suppose that I don't have that. I have two channels. Both of them contain the desired signal. What do I do? Okay? What do I do? Let's think about it. Okay? So out of place, I will delete all of that. Okay? So now we proceed that we don't have what we call a clean, sometimes we call it a clean reference channel, even though it's noise, only noise. Because a clean reference channel, when we talk about reference channel, we mean that it contains only noise. And if it contains the desired signal, we say it's not clean enough, even though it's the opposite, like it's only noise. But this is the way we speak, because for the reference channel, if we have the desired signal in that channel, it means that it has something that interferes with our filter. That's why when we talk about clean reference channel, it means that it contains only noise. Okay, so now we talk about the problem that we don't have a clean reference channel. It contains some part of the signal. So let's assume that we have Y F equals to XF plus VF. This is the main channel. And we have a reference channel, another channel. Let's call it YRF. So it's another channel, reference. So we would like that this reference channel will contain only noise. Of course, not the same noise. If we have the same noise, that is great. We just subtract, okay? But we don't have exactly the same noise in the other channel, in the reference channel. So we have some noise, but we have also some level of the desired signal. Usually it's low, but we have something. So we can write here, let's write it as GF, XF. Usually G is small, because in the reference channel the desired signal is much lower. But we make a general estimation here, okay? Plus noise. Oh, okay, we use W for the filter, so let's use something else. Let's call it VR, okay? This is the noise in the reference channel. Okay? What do we do? If we try to do what we did before, it will be, it will create a large distortion at the output, so it's not good. So now we cannot do something like that. So I will show you what we did before. YF, here YRF, and then we want to find a filter. here minus, here plus, and here x hat f. Okay? This is not a good solution. Why? Because if we try to adapt or to find W such that the energy here is as low as possible, what will happen? W will try to minimize the energy here, the variance here, by filtering also the desired signal. So this is a wrong solution. So I said bad solution, okay? So this is a bad approach. This is, it's not good. So what do we need to do? Okay, what do you propose to do? Simple. You know, in mathematics, there is something like that. Okay. Suppose that there is, you know, soon you will have a tea break, okay? So suppose that there is a tea can or bottle or something like that, and you tell to a mathematician and a physician to take the bottle and pour some tea to the glass. And they are in the same room, okay? So the mathematician will come and pour the glass, you solve the problem. The physicist will do the same. Now suppose that you take both of them and you put the bottle next to them, like here. So the physicist will take and pour the glass, pour the tea to the glass, okay? The mathematician will go to the other place and say, this problem I already solved, okay? So he doesn't need to solve another problem, okay? So this is like a difference between a mathematician and people who work with physics, okay? So we know the problem that we solved before, okay? So let's try, instead of solving this problem, let's come to the problem we solved before with the adaptive filter. So what do we need to do? Here we have a reference channel with some desired signal. So what do we need to do? Is to create a reference channel without desired signal, right? And then the problem that we solved before, we know the solution. How do we do that? Okay, so from these two, do you agree that we can create a reference channel, RF, that doesn't contain the residual, doesn't contain the desired source? How do we do that? What? Yes, we can use both of them. Exactly, so we can get the correlation. So the correlation, if we know G, suppose that we know G, okay? So what will we do? Very simple. We will take GF, multiply it with YF, and subtract YRF. Can we do that? Suppose Y and YR are our measurements. And G, suppose that we know how to estimate these correlations. Assume that we know. So what do we get here? GY minus, so this is cancelled, the desired signal. So what we have is G VF minus VRF. Do you agree? So now we're back to the previous problem, that we have two channels. Now we can use Y and R. So we can use the main channel plus reference channel that contains no desired signal at all, only noise. And then we can find solution, but instead of YR, we will use R. So how do we do that? You see, we multiply so we have YRF. So we multiply this with G, okay? We multiply Y with G, and then subtract it. Here it's plus, here it's minus. Subtract the other channel. So here we get RF, and now we find an adaptive filter such that it minimizes the energy or the variance at the output. And then we get X hat T. Okay? Any questions? Okay, so this is a nice approach. Now, to produce R from the two channels, we can write it like this, you see? So we can write RF as GF minus 1 YF YRF. Okay? I write it like this. So this part, which is here a vector, but generally we will show that is we can do it because here we have only two channels. If we have more than two channels, this will be a matrix. Okay? So this is called blocking matrix. So blocking matrix means that we take the multi-channel signals and we create, generally here we create, if we have M channels, M sensors, we create M minus 1 channels that contain only reference, only noise. So this will be reference channels. Okay? So in our case, when we talk about M sensors, so we have M sensors for the frequency F. What we need is to find a blocking matrix and this, okay, so here we have M, and the output will be M minus 1. So here we have RF, and RF is the size is m minus 1 because we want to cancel the desired signal. Okay? So it means that in this m minus 1 channels, we only have reference channels without any signal. And here we can find a filter, WF, and generally here we can add a certain filter. Let's call it H0. I will talk about it. And then here we take plus, minus. And here we have ZF, which is an estimate of X1F. And how do we find this filter? By minimizing the power at the output. So if we minimize the output of the variance at the output, it's similar to minimizing the variance of the residual noise at the output. Why? Because these channels, they don't contain any desired signal. So the only possibility to reduce the variance at the output is by minimizing the variance of the residual noise. So this is all the concept of adaptive filtering, and we will talk about GSC in a moment. Okay? So one of the earliest methods that was used for such a thing, actually even without blocking the desired signal. Actually, one of the earliest methods, in the past, people wanted to measure the heart rate of a fetus inside when prenatal, inside the uterus. So do you know how it is measured today? How is it measured? The heart rate. So you work all in signal processing. You don't ask yourself how maybe sister, mother, how something is measured? You are not curious? You see that, okay? When you go to hospital and a pregnant woman, so they measure the heart rate. So how do they measure? Okay, try to be more curious. So when you see things with signal processing, try to think, okay, how is it done? What do you think? How is it done? How? Okay, so before I talk about how is it done today, I will talk about how it was done long time ago using signal processing. And when you think, okay, long time ago, when was it? Try to find when was it, because it's good also to know some history, when it was implemented. So it was not like 300 years ago, okay? Signal processing. So try to think how it was done in the past and when was it? And what equipment did they use to measure for the measurement? Okay? So when this kind of signal processing was used, they used actually two microphones. Two microphones. So they put one microphone near where you get the desired signal. Okay, you see where we delete all the time. So we want to measure, so this is the main channel. This is the main channel. So we want to measure to find where to put the microphone with the largest amount of desired signal. What is the desired signal? The heart rate of the fetus, yes? Okay. So where to put it? Where to put it? Here, here, here. Where to put? Where do you think? What? Abdomen, but where? Down or up? Okay, it's partially good. Yes, but it's good. Good answer. Most babies, the head is down. So you want to put the microphone close to the heart, which is somewhere in between the shoulders. So if the head is down, you will put it down. But if the head is up, probably you need to put it in a higher place, at the top of the abdomen. Okay? So you need to try where the pulse, the heart rate, the pulse will be strong. So you need to put the sensor, the main channel, where you can get the strongest desired signal. Okay. What is the noise? So we have different types of noise, but what is the main interference? Exactly, the mother heart rate. So what do you need to do? You can add another sensor, another microphone, and put it next to the heart of the mother. So maybe it will have only reference, only the heart rate of the mother, and the heart rate of the baby is negligible. Okay? And then what you need to do is something like that. So if the other reference signal, it doesn't contain the heart rate of the desired signal of the baby or the fetus, so we are good with this solution. Otherwise, we need solution like that. So we need to block the signal. So we need this G, so maybe it's not easy to find it, okay? But what they did in the past, they ignored this part, and they assumed that the other microphone, with the other microphone, we have only the heart rate of the mother. So why don't we just subtract one from each other? Because it's not the same, okay? So the heart rate in the other sensor, it's not the same as the heart rate of the mother in that signal. But they correlate to the same heart, the same source, okay? Same source. So this is how initially, how they did that. So that was one of the early uses of adaptive filtering, which is nice. Now, okay. By the way, for heart rate, sometimes they don't need exactly that it will contain. So it's sufficient that they significantly increase the signal to noise ratio. And then they can listen to the heart rate of the fetus, okay? Because even in the microphone, when they measure the desired signal, the noise, the heart rate of the mother is much more significant. That's why they need to do some adaptive filtering, okay, which is really nice. Now, nowadays, the sensors are completely different. They even you can even take one sensor. You don't need two sensors. How do they do that? Okay, I'll give you a clue. Using ultrasound. How is it possible to measure heart rate of a fetus in the abdomen using ultrasound? Not ultrasound when you take a video of the ultrasound, but ultrasound signal. So I remind you, what do you do with ultrasound? You transmit a signal, you get it back. Okay, so you transmit a signal, you get it back. What happens to the frequency of the signal that is back, received back from the target? It depends on the movement of the target. So we get a Doppler. And using this frequency difference, we can measure the movement. So this movement gives us a measure of the heart rate. Okay? Next time when you see devices, try to think if it's related with signal processing. At least, if it's not related also, you can ask questions. How it is implemented, what is the main concept over there. So it's interesting to know. Okay, now how this is related to MVDR. So this is a very nice way to obtain MVDR differently. Okay, so it's a different expression or different way to achieve MVDR using such a structure. This structure is called GSC, Generalized Silo Construct. There is a very nice paper, only 4 pages. So if you have time, read that paper. Its number in this chapter is number 17. Okay? Only 4 pages about the equivalence of LCMV and GSC. Nice paper. Okay, even though the mathematics is similar to what I show you on the slides, but I think it's really good to get used to read papers when you want to find something. So you see all the paper, you see the structure, how they present the work. So it was published in 2002. Okay, 22 years ago. By the way, it was also developed before, but this, they show a very nice equivalent, so it's a nice paper. So what do? With the MVDR, what we did, we minimize, I remind you, we minimize the variance of X1, the variance of the output, okay, MVDR. We minimize the variance of the output, which is H, F, phi y, HF, subject to distortionless constraint. Now, instead of using a filter, so here the output, Z equals to H Y. Okay? So instead of using this structure, what we did before, see, here we have Y, we multiply with H, we get ZF. So instead of writing H this way, we write H this way. So this is kind of block diagram of the implementation of H. So here we can write H using this GSC, generalized sine-law construct. We write it as H0F minus B WF. Okay, so we can always write something like this. Okay, so it looks like we try to solve a more complicated problem. See? But actually it's helpful, as we will see. But it looks like we complicate the problem instead of simplifying the problem. Usually we look to simplify problems, not to make it more complicated. But the objective here is like that. So we can show how to find H0 and how to find W and how to find B. Okay? So H0 we find such that it satisfies the distortionless constraint. So H0 is such a filter that satisfies any filter, that satisfies the distortionless constraint. The blocking matrix is a matrix of size m by m minus 1, such that we have here m minus 1 channels that don't contain m linearly independent channels. Okay, so this is the dimension. We started with m channels. Now we have m minus 1 channels. So these channels, they don't contain the desired signal. So we call it, actually we call it something like that. So this is blocking matrix because it blocks the desired signal at the output. And the maximum channels that we can get out of m channels without the desired signal is m minus 1. So this is blocking matrix. So this blocking matrix, we can actually obtain it if we know the model, the relative transfer functions, okay? Just like we showed before. So if we know the relative transfer function, which is the steering vector. So we know how to find this blocking matrix. Now, the third part, W, is obtained by minimizing the energy at the output. We minimize the energy of ZF, the variance of ZF. And we don't need to put here any constraint. Why? Why don't we need to put any constraint? Because if we want to minimize this variance, it minimizes, it uses the input that of channels that don't contain the desired signal. So if they don't contain the desired signal, we don't need to put the constraint here because it doesn't apply. W doesn't work or doesn't filter the desired signal. So you cannot distort them. So if we solve this, H, so H0, we can solve this. This, we can solve W. So if we, B, the blocking matrix, we can find from the transfer function, relative transfer function. So instead of solving this problem, minimization problem with a constraint, we solved two different problems. One is this, one is this. B, we can derive it. It's quite easy from the relative transfer function. Okay? And then we put it here, so we get solution. So in theory, the solution of this problem, or the solution of this problem, it's the same in theory. In practice, it's not the same because we have some estimates of the correlation matrices. Okay? So how do we solve this? So you see here, we can have infinite number of solutions. So we can find the minimum norm solution. Okay? Here we can find B, and here we can find, actually let's write it more explicitly. So actually we can find minimum WF of the variance of here, which is H0 minus B. Okay, I will write it like this. phi y H0 minus B WF. Okay, so I can find this, the solution for this, without any constraint. No need for Lagrange multiplier. So I can find W that minimizes this. Very nice. The thing is, the major advantage, to find solution to minimum variance, we use adaptive filter. So all the methods for adaptive filtering, like LMS methods, least mean squared methods, and normalized, and RLS, and all these adaptive filtering methods, we can use it for W. So we can do it online, in real time. We don't need to do something offline, just like we solve here. Also this, we can solve offline, using least squares, okay? But it's better to use, in real applications, to use adaptive filtering methods. All the LMS family of solutions. Beautiful. Don't you think it's beautiful? Very beautiful. Beautiful work. So this is a very nice contribution to array processing. Actually, things like that are used for beamforming, in speech applications, in communication, wireless communication, EEG measurements. So this work made a very significant contribution to array processing. So it's very important. Okay, so we see that GSC gives us a very nice, attractive way to obtain the MVDR solution in real time, adaptive solution, adaptation of this filter. So if we use offline solution, in theory it's the same. But the structure gives us a way to do adaptive solution, which is beautiful. Now, it's possible not to only give a solution or provide a solution to the MVDR, but also to the LCMV. And this extension is very, very easy, very easy. So instead of one constraint with the LCMV, we have multiple constraints. So let's see it on the slides, how it provides a very nice solution. Okay, I see that I had to give you a break like 15 minutes ago. So now it's good time to give you a break, think about it, and then we will continue and show that the GSC also provides a very similar structure to solve or obtain an adaptive solution to the LCMV. Okay? So let's have a 10-minute solution. We will continue at 3:25. Okay? Fine, thank you. How are you?
Had your lunch?
Hmm?
Lunch. Had your lunch?
Ah, yes, yes. Okay. Does it work? Need to-
I think that is on.
because instead of one constraint, we have multiple constraints. So what do? We can write the filter as two components, what I called here H0. So we will call it minimum norm. We will see. It doesn't really matter how do you call it. But instead of finding this filter, we find two filters. One is H0 or HMN, minimum norm, and we find another filter here. So the objective is to find a filter here without needing to add the constraints. So we separate this structure into two things like this. One, the top, is just to find a solution that satisfies the constraint. And at the bottom, we find the solution of the filter that satisfies the minimization of the power or the variance at the output. This is the idea. Okay, so the minimum solution, so we just need to satisfy the constraint. So for the LCMV, what is the constraint? The constraint looks like C, the matrix of constraint, H, minimum norm, or H0 that we called it here. It doesn't really matter. We want it to be IC. This is the vector of the values of the constraint. Just like we saw, this is the constraint of the LCMV. So the solution for this is this. This is the minimum solution, minimum norm solution. Okay? And so we have a solution to this one. Now the blocking matrix, we can obtain it such that we will have, if we have C constraints or MC constraints, if we have MC constraints, so the number of channels here will be M minus MC. Okay? So we need to find the blocking matrix. Okay? So the blocking matrix is actually the matrix that spans the null subspace of C. So we need to get it from here. How do we find? You see, in this case, in the MVDR, it was what we wrote before, okay? So it's a blocking matrix. We showed an example how to block the desired signal. So actually, if we know the steering vectors, we know the steering vectors of the constraints. So we know the matrix C. So we can find a blocking matrix of size M by M minus MC, such that this will be satisfied. So actually, we say that the blocking matrix, spans the null subspace of C. This is the way to tell it, okay? Because this is satisfied. Now, so we can find a solution for that, okay? What is the solution? The blocking matrix. Okay, it looks like that, just like we showed before. So the blocking matrix can be written as a matrix P, PC, and this matrix is identity matrix of size M minus C by M minus C. This is the identity matrix. The rest are 0. And this is a matrix that projects the input. So it's a projection input. This is a projection matrix that projects the input signals here, project it onto the null subspace of the constraints. Okay? So of course you can see what is the solution, but this is known. What are the projection on a space? If you're not familiar with subspaces, signal subspace, null subspace, and projection onto a subspace, I can give you a very good reference to read. So there is a book which is called Mathematical Methods in Signal Processing. Okay, so it's a very basic book, more than about 20 years ago, maybe slightly more, which will give you all the basic mathematics of signal processing. So if you're not familiar with this null subspace and the projection onto subspace and so on, it's important to read this stuff if you're working with signal processing and array signal processing, image processing, EEG, and other types of signal processing, also machine learning. You will need that. Okay? So this is a way to write it. Okay, so we can find, you see, so if we know the constraint matrix, if we know C, we know B, just like with MVDR. With MVDR, if we know the steering vector, we can find, we know what is the blocking matrix. This is the only information that we know. So if we know the steering vectors here in the constraint, we know how to project to the null subspace. So the rank of this null subspace of C is M minus the number of constraints. So this is the rank of the subspace. So we can immediately, we can get very easily the blocking matrix. By the way, it's not the only solution. There are other solutions. And there are some works about finding a better way. Because which solution out of the, that when it's just like basis functions. See, when you span a space, you can span it using different types of basis functions. For example, just like time domain, frequency domain, time frequency domain, so on. So you can find basis functions that span your space of signals. So also, you can find different blocking matrix that span the null subspace of the matrix C. So this is just one solution, but it's not the only solution. So there are some works that compare different solutions and try to find for different applications how to choose this blocking matrix. But just here, I want to give you just one of the solutions. So we found B. We found H minimum norm. We found this. We found the blocking matrix. Now we only need to find W such that we minimize the variance at the output without any constraint, because we already satisfied the constraint here. So we don't need to find W with additional constraints. So it's unconstrained minimization, which is much simpler. It's just like adaptive filtering. So we can either do offline, but there is no advantage of doing offline, because if we do offline, we can find a solution of the LCMV. But we can do it online with adaptive filtering. So it gives us the flexibility of implementing LCMV with adaptive filtering. Okay? So we minimize here, and we get, this is the offline solution, but we can find solution using adaptive filtering. Okay, and then we have, this is just the mathematics to show different derivations, to show the equivalence. This is the implementation with STFT. I talked about it yesterday, so we can skip. And this is the reference number 17, which is only like 4 pages, which is very nice to read. So I recommend you to read this paper about the equivalence between LCMV and GST. So you see, try to read papers which are interesting. It will give you inspiration in your research. Okay? Okay, now we move on to fixed beam forming. Before we move on, I will show you a short clip. Actually, I have two nice short clips. Okay, I'll show you. Okay, I have a few interesting clips. Okay, first I want to show you what is signal processing, so you know, but you'll see maybe some applications which are very important and you don't know. And then I'll show you maybe also benefits of spoken language technology. Show you two.
What is signal processing? Signal processing is a branch of electrical engineering which pulls meaning from the broad sources of data that are all around us. But what does that mean exactly? It means signal processing is at the heart of our modern world. Signal processing powers modern communications,
How can I help you?
modern entertainment, and tomorrow's transportation. Signal processing is at the intersection of biotechnology.
Voice print access.
Access granted.
It's in our social interactions. Learning to anticipate our needs and emotions. Helping us hear the world around us and to better understand it.
سلام چطوری خوبی؟ Hi, how are you doing?
To bring new life and help us heal. Signal processing brings the world to our homes, adds clarity, and puts it in our pockets. Signal processing documents our cherished memories, helps to keep us safe, and powers the world of finance. Signal processing, processing the future.
Okay, so you can use it when somebody asks you, what do you do? So you can talk about, and I'll show you another nice video about using speech with deep learning and machine learning. This is also a nice clip.
Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger? Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger?
What's a Leon burger?
It's a big dog.
Did you guys leave a window open when you recorded this?
You got a problem with that? I'm doing a murder mystery, only there's too much wind noise, so we have to redo a key line. But this isn't about Leon burgers or murder mysteries. It's about signals and computers that learn. But you knew that from the title.
Just for fun, read it completely flat.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Brian King was an intern when he helped develop this automatic dialogue replacement program that fixes the wind problem and my purposely crummy read beautifully. Brian's software will make my voice match the original read exactly. Normally this would take you an hours to match, and it still wouldn't be very good.
I heard that.
Car scene, take one.
And action.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Very impressive. So what role does signal processing and machine learning play in this program?
So it's really a two-step process with that.
Just I want to mention that something like that with classical signal processing was a big, big problem. But with machine learning and combining signal processing and machine learning, now it's possible to do things which were thought as almost impossible. And I have many examples like that in many areas. So that's why I encourage you to learn signal processing and deep learning, machine learning methods, and then combine them. Because I think in our area, this is the future of working applications and theory, combining application and theory, and mathematics and the physics part to understand the models, and also to use machine learning to combine to get solutions. Actually, it's related to what we did, adaptive. So with machine learning, you adapt the parameters of the models to achieve a certain results. So it's quite amazing, see, what they showed now.
Signal processing part, we're taking these audio signals, so your speech, and analyzing it in such a way that we can figure out the important parts of the signal. And then the machine learning part is aligning those features kind of every step in time. The coolest thing is being able to do things that have previously been impossible to do and no one's been able to do before. It's a little bit like magic.
Brian told me about another application of signal processing and machine learning where instead of using sound waves, they're using brain waves. Xin Zhang is trying to tell the computer to move this arm brace using his thoughts. What are you thinking about to make the arm move?
Just grasping my hand.
Grasping your hand,
Yeah.
and that allows it to bend.
Yeah. Yes.
He doesn't have to grasp his hand, he just thinks about doing it. There! That's not him moving his arm. That's the arm brace receiving his brain signal from the computer. Xinyi Yang heads up this brain-computer interface project. Why do you choose to use the action of grasping to move the arm?
Studies have shown that if you imagine a hand movement, it will create some very distinct changes in the EEG signals.
And how does signal processing play into this whole thing?
First, we can use signal processing methods to analyze the signals to look for specific patterns that occur when you perform a movement. Another very important application is to remove noise from the brain signals. The third one is to extract important information from the brain signals. The machine learning will try to distinguish different brain patterns. It will be able to distinguish whether the person is imagining a movement or he is resting. We can use this technology to help people with limited mobility to operate certain devices, for example, a prosthetic hand or a wheelchair or a computer. If you can't use the keyboard, you can use this technology by using your brain signals.
There's another recent development that couldn't exist without signal processing and machine learning.
What do you do for fun?
¿Qué haces para divertirte?
Li Deng and the team at Microsoft came up with this translator. With this, he spoke with me in his native Mandarin. What's been the biggest challenge in creating the Skype translator?
最大的挑战是实现高精度的语音识别和机器翻译。
The biggest challenge is to achieve high-precision speech recognition and machine translation.
语音识别是一个核心的信号处理的问题。
Speech recognition is a key signal processing problem.
将机器学习应用到语音识别，精确度大大提高。
Machine learning has been applied to speech recognition. Accuracy is greatly improved.
Where in the world do you wish to travel?
By the way, there are some devices now that on a wearable device like glasses, people who don't hear anything, so they can listen to somebody and they get the translation of what the person says, and it's possible in any language, even if they don't understand the language, and it's put on the inside, on the screen, on the glasses from inside, so they can read what he says. Think about now there are unlimited applications that people are working on, companies, and you can be part of that. So amazing, amazing devices, okay?
¿Dónde en el mundo te gustaría viajar?
A Rusia.
To Russia.
¿Y tú?
And you?
Everywhere.
In this translator and our other two examples, signal processing algorithms processes and extracts information from data, while machine learning algorithms recognize patterns and make recommendations. Signal processing is prevalent in thousands of humanities tools, like cellular communications, financial markets, aviation, radar, medical imaging, robotics, and digital videos. Machine learning is prevalent in a large number of prediction problems, like weather forecasting, games, search engines, traffic patterns, social networks, and recommending movies you'd like to watch or books you'd like to read. Everything in the universe can be described as a signal in the form of a wave. Vibrating stars, vibrating quarks, even vibrating Leon burgers.
Okay, now we move on to fixed beamforming. So I will show you that now after you learned also the main things in array signal processing, now the rest, or what I'm going to show, I'm going to talk about fixed beamforming and adaptive beamforming. But instead of doing all over from the beginning of what is fixed beamforming and so on, it's just like the mathematician. I need to show you the differences between fixed beamforming and what we learned about signal enhancement, multi-channel signal enhancement. Once you know the differences, what we did before is applicable to fixed beamforming. It's applicable to adaptive beamforming, okay? So everything, now the rest of the talks, the other topics, fixed beamforming and adaptive beamforming, is just derivatives of some of what we already talked about in length. So it will be much shorter. I'll just talk about the differences. Okay, but this is what is important, because you are familiar with the mathematics of signal enhancement. So I'll show you the differences, and then the mathematics is very similar. That's why it's important to study related areas and problems, because you can apply one to each other, and you can learn from one to each other. Okay, so the signal enhancement problem, let's talk in the frequency domain, because now after we talked about time domain, we'll do fixed beamforming and adaptive beamforming in the frequency domain. If you like to do it in the time domain, you will also know, because you're familiar with the methods. Okay, so for simplicity, we will work in the frequency domain. So we have M channels. So we have a vector of measurement for each frequency, and we assume that we can write it as x1f multiplied with a steering vector, because it's a directional source, plus noise. I will put here be like this. This is the vector of noise for the frequency f in all the M sensors, okay? And then we try to find an estimate of the desired signal in the reference channel, the reference sensor, by obtaining a linear filter that looks like this. And we found various methods. We defined performance measures and obtained optimal filters according to these performance measures. So this is signal enhancement. Okay, multi-channel signal enhancement. Now, which information did we use? Okay, so we used information about the relative transfer function. This is the information that we use. Relative transfer function, which is an important part. It contains important information. It means that if we have a source and the array is somewhere, so we know what are the reflections from the propagating wave, how it reaches, how it is measured in the array. So we know this relative transfer function. What do we, additional, what do we know? Okay, what do we know in addition when we find these optimal filters? So we assume we know also Rx. No, we call it in the time domains R. So the correlation matrix in the frequency domain, we call it phi. Phi x. So this matrix, m by m, which means that we know the correlation between desired components from two sensors, any two sensors for the frequency f, every frequency. But we know this correlation. In addition, how do we know this correlation? Actually, I don't need all this matrix, because I know if I know D, it's enough that I know the variance of x1. Okay? Let me write it, okay? So this correlation matrix is the expectation of x so it's actually phi x1, the variance of x1, multiplied with the dh. So if I know D, and I know the variance of the desired signal in the reference channel, I know this matrix. In addition, I assume that I know phi v f. Okay, so you can write it like this. So I know also this matrix. So I know the correlation of the noise components in every two sensors, between the correlation between any pair of two sensors, which is also, it means that I know what is the environment, the background noise in the environment. I know, using the sensor array, I know how they received or how they correlate between two sensors. So this enabled me to obtain an estimate of the desired signal in the reference sensor. Now, for fixed beamforming, I don't have all that information. I don't know the environment, because I design it with a device or sensor array without knowing the environment. Afterwards, I put it in a different environment, but I don't know anything about the environment. What I do know, okay. So here, I know that the relative transfer function. Here, I don't try to estimate the desired signal because I don't know what is the desired signal. So what I try, the model is different. So the model is that I have a signal from a certain direction. So I have a signal from a certain direction. Let's call it even, okay, we will call it x1f. From a certain direction, but here I don't use the relative transfer function because the relative transfer function requires to know the environment, the source, how the propagating waves, heat, surfaces, reflections, room, reverberation of the room, and so on. All that included here. So I don't use this. I use a simple far-field propagation steering vector without any reflection. So I will call it f cosine theta. Okay? So it only in three-dimensional, okay, it depends on theta and phi, okay, the direction. So I only know the direction of the desired source. That's it. I need to know the direction of the desired source. Plus noise. I don't know the noise. I don't know what type of noise I will have. So, okay, so what can I do? What can I assume? How to proceed with this problem? So first, what I will try to do, that if I will try to estimate ZF, I will try to apply a filter to Y. But I don't know what are the characteristics, what is the statistics of the desired signal. But I know the direction, and I don't know the reflections. So I don't take the reflections into account. So what I require, that if I apply the filter that I find to the direction, to signal that comes from that direction. So this is the steering vector, far-field steering vector without any reflections in the environment. So I know that. I know how to find this steering vector. We talked about it when we talked about overview, but I will show you. It's enough that I know the position of the array, the configuration of the array. Once I know the configuration of the array, I can find this steering vector. But it's different than this one. This contains a lot of more information of the environment. Here I don't know the environment. I just assume that the desired source comes from a certain direction. Theta 0, let's call it theta 0, okay? Theta D, theta desired. From a certain direction, theta D. Now, in order that a signal that comes from this direction will not be distorted, I will require that this is 1. It's constant for all frequencies. So it's a distortionless constraint for a certain direction. But if I put this array in a certain environment, okay, with reflections, reverberation, and so on, it will not estimate x1. It will just not distort the direct path. But the reflections, of course, they will be distorted. So here, using a fixed beamformer, we will not estimate x1. We will get a source from that direction. So in case the environment is without any reflection, this is an estimate of x1. But if in a real environment with the reverberations and so on, it's not an estimate of x1. So you need to understand that. But because we don't know the environment, we don't know the relative transfer function, we just know or design the beamformer towards a certain direction, theta d, this is what we apply. So this is the distortionless constraint, which is different than what we used here. In addition, I don't know what is the noise environment because I designed it in advance without knowing the environment. So what I can do, I can try to design it relative to certain environments. The simplest environment that I can design it to is either when I have white spatial noise or when I have diffuse noise. These are the simplest environments. Because what does it mean, white spatial noise? Like thermal noise. So we always have some thermal noise. And diffuse noise, it means that the noise comes from all directions, or it means that I don't know where the noise comes from. Because in the real environment, maybe it comes from this direction. I don't know. So I assume it may come from any direction. But of course, you can assume a different noise field. For example, you can assume that the noise comes from all directions like a cylinder, from horizontal directions. But you don't know which direction, so you assume that it can come from any direction in the horizontal plane, but not from any direction, three-dimensional sphere. It's also okay. But you assume something. So regarding this noise, I assume phi v is known for certain environments. Usually, we assume either white noise, white spatial noise, white noise field, like thermal noise, okay? Or diffuse noise, or you assume other things, okay? But for here, just for simplicity, we will assume either this or combination of this. So we can continue from here. Once we understand these differences, now we can take the solutions that we did here to here. But the performance measures, can we define mean squared error? Actually, we cannot define mean squared error because it's irrelevant. Because we don't know the signal. We don't know the variance of x1. We try to do it. So we need to define performance measures and find optimal fixed beamformers based on this information. Okay? This is the most important thing, to understand what is the problem, what we know, and how to proceed. Any questions? Okay. So now, everything will be much simpler. We will define the signal model and problem formulation. We will talk about linear array model, performance measures, spatial aliasing, and fixed beamformers, which are optimal based on the definitions of the performance measures. So this part will be quite straightforward. Okay, we will talk about it because we understand what are the differences and we know the solutions that we did with signal enhancement. Okay, so this is the model like we did before. So first we define the steering vector for a certain direction. This is the steering vector for a certain direction. For this kind of array, uniform linear array, just like we did before. So we assume uniform linear array with inter-element spacing equals to delta. And the signal comes from a certain angle, theta. And then, because we don't have any reflections in the environment, so this is the steering vector that assuming that we have a free field, no reflections, only delays. You see, only delays. So for fixed beamformer, because we don't design it to a specific environment, we assume only that it's like far field direction. Okay? Important to understand the differences. So we call it df cosinus theta, because it depends only on the direction. Now our model is like this, that y equals to d multiplied with x. Actually, it's the same as x1, you see, because the steering vector here, it's always the reference channel. If the first one is the reference channel, we will always have here 1. The others are just delay in time, which in the frequency domain is exponential, that looks like that. So this is our model. And we don't try to estimate x. No. This we tried with the signal enhancement. We don't know how to estimate the signal. We just want that the beamformer will not distort the direct path from a certain direction. But we want to suppress noise as much as possible. Okay? So even here, we assume that when we apply the beamformer, now instead of filter, with signal enhancement, we call it filter. Here, we call it beamformer. It's just a name, because here we talk about beamforming, but when people say beamforming or beamformer instead of filter, it means something. Filter, it means that we know information about the statistics of the signals, the desired and the noise. Beamformer, it means that we don't make assumptions about the environment. If we make assumptions about the environment, we'll see. We will talk about adaptive beamformer. We will move on. But first, I want you to understand. Beamforming, it means that we know the direction. We don't know the relative transfer function. And we don't know the signal, the statistic of the signal. We just want to keep this direction without any distortion, the direct path, without any distortion. Okay. So this is the model. Let's continue, just like we did. Let's compute the correlation matrix of y. So the correlation matrix of y is variance of x, which we don't know, d transpose conjugate, okay? D we know, because we know we will design the beamformer that this direction, any signal that comes from this direction will not be distorted. Plus this correlation matrix of the noise, which we don't know. That's why we will optimize the beamformer with respect to white noise, maybe with respect to diffuse noise, maybe with respect to combination, and so on. Okay? Because we need to assume what is the noise environment. We don't know. Now, linear array model for beamformer, so it's just like that, similar to what we did with the signal enhancement. So we have two components of the X filter desired plus residual noise. Okay? But we don't make any assumptions about the desired signal other than it comes from a certain direction. So if we write the filter desired, when we apply it like this. And the residual noise will be the beamformer that is applied to the noise signal. Now we can compute the variance of the output of the beamformer. So it's composed of two components. One is the variance of the filter desired, and one is the variance of the residual noise. Like this. Okay, so when we this is the constraint of the distortionless constraint to a certain direction. You see? And we will define performance measures that will optimize the filters, the beamformers, under certain conditions. Okay? So performance measures. We will define performance measures. The performance measures will be different than the multi-channel signal enhancement. Because here, performance measures are for a certain given environment and for given signals. Because we know, you see, we don't just know the relative transfer function, which we need to know the environment, but we also know the variance of the desired signal in the reference channel. And we know the correlation matrix. Here we don't know. So we need to define maybe other performance measures. For example, MSE, we cannot define. We cannot define distortion index because it depends on the signal. We don't know the signal, or things like that, okay? So we will see which performance measures we are able to define now for this problem, and how to optimize, how to find optimal beamformers based on these performance measures. Okay? So the most important thing in this till now was to identify, to understand what is a beamformer, what is a fixed beamformer, and what is signal enhancement. It's based on what you know. What are your assumptions? And then we will talk also, maybe you will ask, after you understand the differences and solutions and what do we do with it, you can think, okay, now I have a real problem in practice. I go to my work, go home, I think of a certain problem. Is it better to use a filter that we learned using signal enhancement or a fixed beamformer? After we learn, I will ask you this question, so you have time to think, okay? And then you can give me some answers. When to use each one of them? When one is better than the other, okay? So we will have a break now, and then we will talk about the differences and optimal beamforming method for fixed beamforming. Okay, so you have a tea break. Now it's 4:15. So 10 minutes, 15 minutes, how much do you need? 15 minutes? And then we have another hour, okay? Because I want to talk about that. And then you have your presentations, okay? After my lecture, okay? Undistorted. So generally, we can measure what is the sensitivity. We call it sensitivity. Okay? What is the sensitivity of the array to a propagating wave that comes from a certain direction, theta, other than theta d? Okay? Sensitivity, it means what is the amplitude, the phase, and so on. What is the signal that it will be measured from that direction? So suppose that we design the beamformer such that the signal that comes from theta d, from a certain direction, will be undistorted. What happens if the signal comes from another direction? Maybe we made a mistake. We thought that it comes from a certain direction, but it doesn't come from this direction. It comes from another direction, slightly different. Or we want to know what will be the effect of noise that noise propagates from a certain direction. So of course, if the noise source also comes from this direction, it will be also measured, it will be undistorted, will be measured, will be at the output of the beamformer. But if noise comes from another direction, it will be suppressed, okay? So the first measure is to know what is the effect of the beamformer on a wave that propagates, or signal that propagates from any direction, theta, which is generally different than theta d, okay? So we want to know what is H that is applied to a signal that comes from a certain direction. In three-dimensional space, generally, okay? Theta, maybe theta and phi. But here we work with uniform linear arrays, so we have only one theta is sufficient because we have symmetry over phi. But generally, if we have any tensor array and it's not uniform linear array, we can measure for any direction what is the value. This value means how the propagating wave will be measured at the output of the beamformer. What will be its strength? And we can take this magnitude squared, which says what will be the power of the output of the beamformer for a signal that comes from the direction theta. So this is called beam pattern. This is called beam pattern. And we can take the magnitude squared of the beam pattern, we call it power pattern. But sometimes we call it also beam pattern. Sometimes we call it directivity pattern. All these names interchange. That's why you need to define something. Sometimes people use the same directivity pattern, beam pattern for the magnitude squared. Sometimes they use for this part. Sometimes they use transpose conjugate of H applied to this. Sometimes they take the adjoint complex conjugate of this. Okay, as long as you define and you understand, it's fine. Okay, so here I can do, here the beam pattern is defined at DH H. Okay, as long as you define it. But usually what we care about is the power pattern, which is, we call this the beam pattern. It's also fine. Another performance measure is the gain in SNR. Gain in SNR, array gain. Remember, what is the array gain? Is what is the output SNR using an array compared to SNR using a single channel. So this is the array gain, the improvement in SNR. Okay? So if we take this model, we see that the input SNR, narrowband input SNR, is simply phi x1 divided by phi v1. This is the input SNR. The output SNR, narrowband, will be the variance of this part. Okay, when you apply, when you apply the H, when you apply H to this part, so the variance that H is applied to this part, to the desired signal, divided by the variance when H is applied to the noise. You see? So it will be phi x1 H F D F cosine theta D magnitude squared. This is the variance of the desired signal at the output of the beamformer. You see I put here theta D divided by the variance of the noise, which is H VV H. Okay, this is the output SNR. So actually, we find that the gain in SNR, which is the ratio, so the gain in SNR, we can write it the gain in SNR, the narrow band, for a beamformer H, we can write it as H df cosine theta d magnitude squared divided by H f gamma VF HA F, where gamma is the normalized correlation matrix divided by phi V1 F. This is the gain in SNR. Okay, so now suppose that we want to maximize the gain in SNR. What does it mean? It means that suppose that we have a free field, no reflections, or we ignore the reflections because we don't know the environment. So a signal that comes from theta d and knows that this is the normalized correlation matrix, so the output SNR will be maximal. So of course, in order to design a beamformer that maximizes the gain in SNR, we need to know the normalized correlation matrix of the noise. But we don't know the environment. We don't know the noise. So we have two options. We can assume that the noise is spatially white. So if the noise is spatially white, in this case, so for white noise, it means that gamma V is identity matrix. What is the size of the identity matrix? M by M, okay? Because we have M sensors. This is for white noise. If we have diffuse noise, so gamma V will be something which we know, we will show. We know the elements, which is nice. So we know these correlation matrices for white noise and for diffuse noise. So what we say, that if we find we can find a beamformer that maximizes the SNR, assuming that the noise is spatially white. Okay? Or we can find a beamformer that maximizes the signal-to-noise ratio, assuming that the noise is diffuse. Or we can take combination. Okay? So these are the performance measures. So the gain, if the noise is spatially white, white noise, so for this case, spatially white noise, we call to this value, the gain, when the noise is white, we call it white noise gain. So this is the name. The gain in SNR, when the noise is spatially white, the name for that is white noise gain. So a filter, a beamformer that maximizes the white noise gain is called white noise gain beamformer. Okay? It maximizes. So this beamformer, it maximizes the white noise gain. it obtains the maximum SNR when the noise is spatially wide. If the noise is diffuse noise, then the gain in SNR, under the assumption that the noise is diffuse, it's called directivity factor. So we call it directivity factor. So a beamformer that maximizes the output SNR in case, assuming that the noise is diffuse, it's called beamformer DF or max DF. We can call it, by the way, max. We can call it like this. Maybe we can call it max white noise gain or max DF. So it doesn't really matter. You can call it something, but at least you understand what you call it. Okay? So we will show, which is something that is very interesting. So you can say, why do we assume that we have spatially white noise, thermal noise? Maybe we will assume, maybe we can find a beamformer that maximizes the gain both for spatially white noise and diffuse noise and other types of noise. So it will be optimal. So we will see that we have a trade-off. If we try to maximize the gain for white noise, then it will decrease the gain in SNR for diffuse noise, and vice versa. So when we increase the performance, the output SNR for diffuse noise, it decreases for white noise, and vice versa. So we will see the relations between them, which is interesting. Okay? So what we will see this in many of the things I already talked about. So the gain in SNR, we saw the formula. So the expression is like this. This is the expression. And the definition for white noise gain is when we put here identity matrix. So this is the gain in SNR when the noise is spatially white, which means that the correlation matrix is the identity matrix. And directivity factor is the gain in SNR when we take this correlation matrix of the noise obtained by a certain derivation, and we know how it looks like for diffuse noise. And actually for diffuse noise, the elements of this M by M matrix, it looks like a sinc function. A sinc function, anyway, when you take a sensor array and you have diffuse noise, the correlation between sensors depends on the wavelength, okay, which is the f and speed of propagation, and the distance between, actually the ratio of the distance between the sensors relative to the wavelength, which is very nice. Actually, it can be proved. You can get the mathematical expression, which is a nice proof, if you like to go over that and see the proof or prove for yourself. So this is nice. By the way, this is for spherical diffuse noise. If you have a cylinder of diffuse noise, so it comes from all other directions, but not from the top and the floor, so it's different, okay? And there are derivations for that, how it looks like. But the thing is that once we assume either spatially white noise or diffuse noise, we know the correlation matrix. But in a real environment, we don't know. So we assume a certain noise environment, and we use it to design the beamformer. Because this is what we assume. These are the assumptions that we make for designing fixed beamformers. All these derivations, you can go, it's just to play with that, okay? Any question? So we define the performance measures. So we can talk about spatial aliasing. We know about temporal aliasing when we talk about sampling a continuous signal. So you know when you sample a continuous signal and you take the samples, the time delay between samples should be small enough, or the frequency, the sampling frequency should be high enough. It should be at least, generally, at least twice as the maximum frequency in the signal. So if it's at least twice of the highest frequency in the signal, then it means that we can either reconstruct the signal, the continuous signal, or any two discrete signals that are sampled. If they are different, it means that the continuous signals are also different. So this is an alternative way to say that we can reconstruct the continuous signal. Okay? So if the sampling interval is small enough, or the sampling frequency is large enough, at least twice of the largest frequency, it means that I will write it, because it's a different way. If you're not familiar with that, it's nice to write it regarding spatial aliasing. So I can write, suppose, okay, what is aliasing in the time domain? Temporal aliasing. Okay? Suppose that I have two signals, two continuous signals. So I have one signal, f, as a function of a continuous parameter. Let's call it alpha. Okay? So it's a continuous. And I have another, alpha is continuous. And I have another signal, G alpha. Alpha is continuous, okay? Like here. You don't need to write. Now suppose that I sample these functions, continuous signals, with a certain sampling interval, which means that I find the values of ft with a certain sampling interval, t, like this, ts, let's call it ts. It's the sampling interval. And t is an integer value. T is an integer, so you see instead of continuous signal, you have digital signal, sampled signal. And here we have sampled signal, t, multiplied with ts. Okay? These are the sampled signals. And suppose that the sampled signals, so I ask you a question. What is the requirement on TS? What is the requirement on TS such that if I will write it like this. If f alpha is different than g alpha, it implies that f t ts is different than g t ts. Okay? So what is the requirement on t, the sampling interval, such that any two continuous signals if I sample them with the sampling interval Ts, they will generate sampled signals that are also different. So this is the Nyquist requirement, sampling interval. So the sampling interval should be such, okay, or 1 over Ts. This is the sampling frequency, Fs. It should be at least twice as, okay, I use F here and F here, okay. So let's call it F max, okay? So this is the maximum frequency in these two signals. So if the maximum frequency in these two signals is F max, and the sampling frequency is at least twice of the maximum frequency, so this is satisfied, okay? This is Nyquist theorem. Similar thing we have with spatial aliasing. So what we require is that if we would like to know for our special case, suppose that we use uniform linear array. So we use uniform linear array. And the inter-element spacing is delta. This is uniform linear array. And the spacing between two sensors is delta. So the question is, you see, if delta is small, then we don't have aliasing. So we ask ourselves, what is the maximum of delta? So if we increase delta, maybe we will have aliasing. Okay? So we ask ourselves, what is the maximum possible delta such that any two signals that come from different directions will be different? Because if the steering vector for theta 1, for a certain direction theta 1, and for a certain direction theta 2, which are different, if they are the same, it means that for these two signals, we will not be able to distinguish between these two signals. So if we have high gain, high sensitivity, or high SNR for theta 1, we will also have high SNR for theta 2, because we designed the beamformer for theta 1. So we will get also high SNR for theta 2, but we didn't mean to do that. We meant to design the beamformer such that it's optimized for a certain direction, not two directions. So to prevent spatial aliasing, we require that if two directions are different, the steering vectors will also be different. So for uniform linear arrays, this is achieved. So we require that for any two directions that are different, the steering vector will be different. This is achieved by requiring that delta divided by lambda is smaller than half. Okay? Delta divided by the wavelength is smaller than half. And of course, we need to do it. Okay, so delta is smaller than half of lambda minimum, which is like the highest frequency, you see? It's related to the highest frequency. So you see the similarity between temporal sampling. So temporal sampling, it means that the frequency, the sampling frequency, is larger or twice of the maximum frequency in the signals. Here, so we have the minimum lambda, so we can say that 1 over delta, see, this is the spatial sampling, is larger than twice of 1 over lambda min, which is the maximum spatial frequency in that direction. See, so it's very similar. So this spatial, what do you do with other configurations, not uniform linear array? So you can find the same. So this is the requirement. The requirement is that for 2 different directions, we will not have the same steering vector for those directions. This is the requirement, because this produces aliasing, because we will not be able to identify these two between these 2 directions. Okay, now let's talk about optimal fixed beamformers. The important fixed beamformers. We talked about delay and sum. What does it mean, delay and sum? So delay and sum, actually, it means that we have constructive summation. So suppose that we have an array, and a signal comes from a certain direction, x. So it comes, and this is the first sensor, and second sensor, and so on. So we will delay the signals compared to the first one and take the summation, and then we know that signal that comes from this direction will not be distorted. This is delay and sum. But actually, we can show that the delay and sum beamformer, it is obtained from maximizing the white noise gain. And this is a beautiful way to say it, that the relation between delay and sum and the white noise gain. And I can also explain why, the intuition behind it, in a minute, just a minute. But before, we want to understand the formulation. So how do we achieve the maximum white noise gain? So maximum white noise gain, we want distortionless response to a certain direction. So this equals to 1. This is the distortionless constraint to a certain direction of the desired direction. And then we want to minimize this, when the noise is white, which means that this matrix is an identity matrix. So you see, minimizing this denominator with identity matrix is minimizing H transpose conjugate H, subject to the distortionless constraint. So this beamformer maximizes the white noise gain. Very simple. Why? Okay, so we can find the solution. Very easy solution. This is the solution. So it's D divided by M, which is very nice. Actually, D divided by M is the delay and sum, because each element of D is just a delay. So it compensates. You see a steering vector, which means that it's signal that comes from theta D. If this is theta D, signal that comes from theta D, it comes with a delay with respect to the reference sensor. So the beamformer compensates for this delay, because you see, we take H transpose conjugate. So it's complex conjugate for exponent with a delay. So the sign with the exponent becomes, instead of minus, becomes plus. So it compensates exactly for this delay. So the opposite, okay, opposite of the delay. So taking D up to, this is a normalization factor. But if the beamformer is simply the steering vector, it means that it compensates, exactly compensates the delay for a signal that comes from theta D. That's why this is the delay and sum beamformer. But why delay and sum beamformer is obtained from maximizing the white noise gain? Okay, let's think. Okay, think that we assume that we have a propagating wave from a certain direction, and the noise in all these sensors is simply thermal noise, uncorrelated noise. So if we have uncorrelated noise, think that if it comes from this direction, from the broadside direction, how can you minimize the variance of the noise? Okay, so for a certain direction of the signal, theta d, you have constraint, distortionless constraint. No distortion. And you want to minimize the noise, the thermal noise. How do you do that? By averaging. That's why the lens sum maximizes the white noise gain, because it maximizes the output SNR when the noise is uncorrelated. Because it just takes the values of the signal with compensating the delays between the sensors for the desired signal, and take the summation. Because the summation, this is the best that we can do in order to suppress as much as we want, as much as we can, the white noise. That's why, by maximizing the white noise gain, we get the lens sum beamformer. Because we just delay. Actually, it's just, we call it sometimes, for the delay sum, is a steering beamformer. Because we just steer the beamformer towards the direction theta d. That's it. This is the best that we can do for this performance measure. Maximizing the white noise gain. Okay, so we can we can derive some mathematics behind it. But I don't want to go into all the other things. I want to continue and talk about, so this is just show some relations. Okay, let's see an example. Consider a uniform linear array with M sensors, and suppose that a desired signal comes from the direction theta d. And then we want to see what happens to the white noise gain. Okay? Let's see here in this figure. We see what is the white noise gain for the signal that comes from theta d as a function of the frequency. So what we see that if we use the beamformer, the delay in sum beamformer, actually and we use here 2 sensors, 4 sensors, 6 sensors, and 8 sensors. The more sensors that we use, the white noise gain increases. Because the white noise gain is just the improvement, the gain in signal to noise ratio. So if we use more sensors, we increase the white noise gain, which is the output, the gain in SNR. Also, we see that the gain in SNR is simply M, because this is the maximum possible white noise gain, which is M, and it's independent of the frequency. Here it's in dB, so 3 dB is log is 2 in dB, okay, and so on. And you know that if we measure with M sensors, if we use M sensors, and we have thermal noise, same level of thermal noise in M sensors, and we take the average, what happens to the average of variances? So the variances is reduced by the factor M, which means that the white noise gain that is achieved by using the beamformer that maximizes the white noise gain, which is actually the maximum possible white noise gain, is M, the number of sensors. Because when you take uncorrelated noise, and you take the average, the delay in sum, it will reduce the variance by a factor of M. We know that from statistics. It's very simple. So we see that in this example. What happens to the directivity factor? So the directivity factor, using the delay in sum, we see it for 2 sensors, 4, 6, and 8 sensors. as a function of frequency for 3 different cases. This is one case, this is second case, this is the third case. In this case, theta d is 90 degrees, which means that the source, the desired source, comes from 90 degrees from the broadside, and the distance between the sensors is 3 centimeters. In the second plot here, theta d, the direction of the source, it comes from the end fire, from 0 degrees. And the distance between the sensors is 1 centimeter. So it looks like this. So you see, for higher frequency, the directivity factor increases in these 2 cases. In the third case, theta d is 0, which means that the desired source comes from the end fire, comes from this direction or this direction, same. But the distance between the sensors is 3 centimeters. And then we see something strange. So initially the directivity increases as we increase the frequency, but then it decreases. So this is something strange. Okay. So directivity, why in these 2 cases do we have an increase of the directivity when the frequency increases? Because what is the directivity? The directivity is the gain in SNR when noise comes from all directions. All directions. So it means if you take the integral over all directions, you want, so for high frequencies, you have a more narrow beam width. So the beam that is steered to the direction theta d is more narrow when the frequency increases. So the integral over all directions becomes lower. That's why when the frequency, generally when the frequency increases, makes sense, we get higher directivity because the mean beam becomes more narrow, and then the integral over all directions becomes smaller. So if the denominator becomes smaller, this ratio, here it's 1, right? So this ratio becomes larger. So the directivity increases when we increase frequency. But here, it increases, but then it decreases, which looks strange. But we know why it happens. So when you see a decrease of the directivity when the frequency increases, you see a decrease. What does it mean? Aliasing. Because the main beam decreases, but then you start to get another side lobe from another direction that increases because of aliasing. And that's why the directivity decreases, because the integral decreases. Because you have a side lobe for a certain other direction that start to increase. Let's see that. So if we check the beam patterns, okay, so these are beam patterns, polar plots. What do we see? So we see here different beam patterns for different frequency. This is for 1 kilohertz, 2 kilohertz, 4 kilohertz, and 8 kilohertz. For the first case that we showed before, 90 degrees, broadside signal, and delta equals to 3 centimeters. So here we see that the desired direction is 90 degrees. So you see that the main beam is directed towards 90 degrees. And as we increase the frequency, the main beam becomes more narrow. It becomes more narrow. The side lobes are low, which means that we don't have aliasing in this case. If we take the second scenario, that the signal comes from 0 degrees, from the end fire, and delta is small, 1 centimeter. So you see that the main beam is directed to theta d, to 0 degrees, to this direction, to the end fire. But here, because delta is small for this case, so still we don't have aliasing. This is 1 kilohertz, 2 kilohertz, 4, and 8 kilohertz, even for high frequencies. Usually we have aliasing for high frequencies. If we continue, for the third case, when we have a source from the end fire, and then delta is 3 centimeters, so you see 1 kilohertz, all the main beams are directed to the desired direction, of course. It's a delay in sum. So it's directed to the desired direction, theta d, 0. But here, for high frequencies, 8 kilohertz, we see aliasing. You see side lobes that grow for certain directions, which means that for those frequency, for that frequency, we cannot identify for that frequency a signal 0 degree and that direction. So it's because the steering vector for 0 degree and this direction, the steering vector are the same. That's why we have the aliasing. So this aliasing for high frequencies, we see it also in the directivity, what we saw before. Here, you see? So for the third case, like this, so up to 4 kilohertz, we don't have aliasing. And afterwards, we have aliasing. So the side lobes start to grow. And then we have a decrease. Any questions? Okay. Now, instead of maximum white noise gain beamformer, we can define or try to optimize, we can find the maximum directivity factor beamformer. How do we get it? By maximizing the gain that we wrote here for diffuse noise. So we need to minimize the denominator in the array gain when the correlation matrix of the noise is this matrix that corresponds to diffuse noise. And of course, we have the constraint distortionless response for the direction theta d. So we can find the solution. So the solution to that, it's very easy to show, just like we showed the MVDR and so on. So this is the solution. Let's see an example, the same example that we saw before. If we go to the same example, but now we use the beamformer that maximizes the white noise gain instead of the beamformer that maximizes the directivity factor instead of the delay in sum. So let's first see the directivity factor. So if you compare the directivity factor, you see we have 3 plots for 3 different scenarios, just like what we showed before. So the directivity factor for this first scenario is when the desired source comes from the broadside and the distance is 3 centimeters. Second scenario is when the source, desired source is, or the steering is towards 0 degree end fire, and the distance between sensors is delta 1 centimeter. The third scenario is when we increase the delta, the distance between sensors, to 3 centimeters. So first we see that in these 2 scenarios, when we increase frequency, generally the directivity factor doesn't decrease, maybe even increase. Here it's almost constant. But here, it decreases when we increase frequency. Okay? So it means that maximum achievable, the maximum achievable directivity factor decreases. Okay? So if when we increase frequency, the directivity factor decreases, it means that we have aliasing. It means that it's because the main beam will be more narrow. So if it decreases, it means that side lobes start to increase. So from the directivity factor, we will see that. Okay. So if you compare the directivity factor that is obtained with this beamformer that maximizes the directivity factor, of course, if you compare it for a certain number of sensors, 2, 4, 6, 8, compared to the directivity factor that is obtained with the Delaine sum, which one will produce with higher directivity factor? The Delaine sum or this beamformer? Of course, this beamformer, because we obtained it based on this performance measure. It maximizes the directivity factor. But it's interesting to compare also the white noise gain. So the white noise gain that is obtained with this beamformer compared to the Delaine sum, which one will result in higher white noise gain? Delaine sum, because the Delaine sum optimizes it, maximizes the white noise gain. So in terms of white noise gain, the Delaine sum is more optimal, is better. In terms of the directivity factor, the beamformer that maximizes the directivity factor is better. Okay? Of course, so we can compare between two, but when you compare, it depends what is your performance measure. Okay, now the question is, this is a good comparison. You see, suppose that we try to maximize the white noise gain, which means that we compute the Delaine sum beamformer. What happens to the directivity factor? So we can see, I will go back, okay, to the other example, because just a minute, I want to go back to the other example, example number 1. Here. Okay, so this is the white noise gain that was achieved using the Delaine sum. So we see very nice, very high white noise gain, of course, because we optimize the white noise gain, so it's the maximum. But what happens to the directivity factor that is obtained by using the Delaine sum beamformer? So it can be proved that directivity factor that is obtained using the Delaine sum beamformer is always larger than 0 dB or larger than 1. It's always larger than 1. What does it mean? That the beamformer, that the beamformer of the Delaine sum beamformer, first it maximizes, what happened? Okay, so the Delaine sum beamformer it maximizes the white noise gain because that was our performance measure, but also it doesn't amplify the diffuse noise. Because the if we amplify the diffuse noise, it means if we amplify the diffuse noise, it means that the array gain for diffuse noise or the directivity factor will be lower than 1. Lower than 0 dB, will be negative. But using the Delaine sum, we obtain very nice results, which means that even though our objective was to maximize the white noise gain, even if we put this beamformer in an environment with diffuse noise, it will not amplify the diffuse noise. So the array gain will not be negative. Negative array gain, it means that it amplifies the noise. Okay, so I repeat. We designed a beamformer, a fixed beamformer, for thermal noise environment, for white noise. So we try to maximize the white noise gain. And instead of putting it with this thermal noise environment, somebody took it and put it in another environment that we didn't design. We put it in a diffuse noise environment. So the noise at the output of the beamformer will not be stronger than the noise in the reference sensor. This is a result that can be proved. Actually, it's in one of the slides. You can see the proof, which is nice. But what happens with the other beamformer? So the other beamformer is the beamformer that was designed to maximize the directivity factor. Okay, so where is it? This one. So this beamformer was designed to maximize the directivity factor. So somebody took the array, he designed a beamformer, assuming that he knows the direction of the desired source, and he tried to find the beamformer that maximizes the directivity factor, which is nice. It means that the directivity, the gain in SNR, when you have diffuse noise environment, the directivity factor, the array gain, will be high as possible, the maximum possible. Which means that if we design this beamformer and actually we put the array in an environment with diffuse noise, it's optimal, the best one in terms of gain, array gain. Now, if somebody takes this beamformer with the array and put it in a different environment, instead of diffuse noise, you have thermal noise. What will happen? So what will happen? We need to check what happens with the array gain, white noise gain. So what is the white noise gain when we use a beamformer that maximizes the directivity factor? This is interesting because we don't know the environment. So we designed a beamformer for diffuse noise, and then somebody takes it and put it in an environment only with thermal noise. By the way, there is always thermal noise because the sensors are never perfect. They always contain some thermal noise. Okay, so white noise gain means that we take the array and we don't have diffuse noise. We only have diffuse noise. What happens to the array gain? You see the number here? The numbers. Minus 60 dB, minus 40 dB. It's huge. Okay, it means that it's very small. It means that if you use this beamformer that maximizes the directivity factor, and you take the beamformer with the array, put it in an environment with thermal noise, it will amplify the noise, the thermal noise. If it's minus 60 dB, it means that it will amplify the noise by 60 dB, which is huge. Okay? So you see the differences between delaying some beamformer and a beamformer that maximizes the directivity factor. So if you design a beamformer that if what is important is the thermal noise gain of the beamformer, the array gain under thermal noise, and you design the maximum white noise gain beamformer, at least if you put it in an environment, a different environment with diffuse noise, you don't amplify the noise, which is okay. But here, this is a very problematic because you need to consider what will happen with the thermal noise. Sometimes you want to consider some design, how it behaves in another environment. We call this, how do we call this? Design robust. What does it mean, robust design? It means that we make assumptions. And if the assumptions are inaccurate or false, we change. If the assumptions change by some degree, some error, we want to see if our design is still okay, if it works well, if it doesn't degrade completely. So it means that our design is more robust to some error. So we see here that the maximum white noise gain beamformer is robust to noise environment, to diffuse noise. It's robust also to diffuse noise because it works also in diffuse noise environment. But otherwise, the beamformer that maximizes the directivity factor is not robust to white noise. Okay? So it means that if you want to achieve high, like this, just a minute. So if you want to achieve high directivity, don't try to achieve the maximum. Maybe try to achieve something smaller to make it more robust. So we will talk about robustness of beamformers, which is a very important concept, robust beamformers. But before that, I just want to show to this example the beam patterns. So you see, this is for the first scenario. You see, in the first scenario, we have increasing directivity factor as the frequency increases for these two scenarios, but not for the third scenario. So in the first scenario, we see this is the frequency, 1 kilohertz, 2 kilohertz, 3, 4 8 kilohertz for the first scenario. First, if you compare it to what we had with the maximum white noise gain beamformer, you see that with the maximum directivity factor, we obtain much more narrow main beam, more narrow. So it means that these beamformers are more directive. That's why the directivity factor are higher. If we take the second scenario, it looks like that. So you see it's directed towards the end-fire direction. And the beam width, main beam, is more narrow than that of the maximum white noise gain beamformer. In the third scenario, you see the aliasing. Okay, so you see side lobes that are large. So you see aliasing. That's why you have decreasing value of the directivity factor when you increase the frequency. Any questions? Okay, so tomorrow morning we meet at 9, okay? So if something is not clear, try to read the things, but we will continue from here. We will continue about how to make the maximum directivity factor beamformer robust. What does it mean robust? That it can handle also thermal noise, which means that if we look at the white noise gain, we want to limit the white noise gain so that it will not become lower than a certain threshold. So what we will do tomorrow, we will talk about robust maximum directivity factor, which means that we minimize this for correlation matrix that corresponds to diffuse noise, but we also require that the white noise gain will be larger than a certain threshold. This will make it robust. And of course, when we add a constraint, always in optimization, when we add additional constraint, we sacrifice something. So we sacrifice the directivity factor. So the directivity factor will be slightly lower than what can be achieved with the non-robust. But we want to satisfy that it will be robust to thermal noise, which is very important. Okay? So now it's time for your presentations. Maybe 10 minutes break, or you want to start with your presentation? It's up to you. So either we start with your presentations, or you have a break. I think maybe start the presentations. Okay, so let's start with the presentations, and then we meet tomorrow morning. Okay, take this.
laser okay. Good evening.
Good evening, sir and madams.
Good evening. This is Prabhakar Rao from Ranchi. My coordinator, Dr. Vinay Kumar from JNT Kakinada. We'll be talking on speech de-reverberation. What is reverberation? Then what is de-reverberation? What's the importance of the models on speech de-reverberation? So this is what I'll be introducing. Later, Dr. Vinay will take it up. Looking at this, okay, it's not working. That's what. Sometimes, okay. Thank you. Looking at this image, you might be understanding what it is. This image is taken from the book of Professor Israel Cohen, Speech Processing in Modern Communications. So here we see the word reverberation, and this is caused by different factors like the sound waves reflected from room and other objects in the room. So when speech is recognized or recorded, when there is reverberation, the clarity, the quality, the accuracy in the speech signal will be lost. Hence, we need to see for the method which will nullify the factor of reverberation. That's where the importance of speech de-reverberation is. So, in his book, reference 3, Professor Cohen says that there is much research in speech denoising, but there is limited research in speech de-reverberation. And we need to find out the models which will nullify the problem of reverberation. So our problem statement, of course it's not written here, can be stated as reverberation, background noise can degrade the speech quality, intelligibility, clarity, accuracy. Hence, we need to formulate and design a de-reverberation model which will enhance the quality, accuracy, intelligibility, clarity of the speech signal. That's the problem statement. Now coming to the assumptions, in order to realize such system, such model, we assume that the speech or reverberation signals are recorded from the signal that is there in the room or that is reflected from the objects. We need to model it, of course. That's the first assumption. That means in a diversified acoustic system, we record the reverberation noisy signals. And second assumption is that we would like to formulate or design a model which will address the problem in the single microphone recorded reverberation systems or else monaural speech reverberation systems, and also multi-channel or multi-microphone reverberation systems. So that is the second assumption we would like to make. And third assumption is we would like to make a robust model which will adopt adaptive techniques or filters which will address the problem of reverberation. Hence, we would like to make an optimal de-reverberation model to address this problem. There are, of course, much research gaps. We have gone through only one paper, but if you go through other papers in general, there are much research gaps. As initially I told, there is much research available in speech denoising, but not on speech de-reverberation. So hence this problem is very demanding. So we need to concentrate on this. We need to think about other complexities or other gaps in the research, like the system complexity, efficiency, all those parameters, and to make our system adaptable to other existing systems. So all these things. Mr. Vinay, Dr. Vinay is not going to present whatever is there in the reference paper 1, but he is going to give a versional model. Of course, we didn't realize it, but a mathematical formulation and everything else he will be presenting. Thank you.
Thank you, Prabhakar. So this is a noisy observation of that we have. Okay, we let S of t is the clean speech, and H of t is the room impulse response, and N of T is the ambient noise. So this is the observation that we have, which is the noisy signal observation. This S of T convolved with the echo-free, that is a direct impulse response. Then we have the echo-free speech, which is denoted as X of T. And here we are convolving the speech with the reflected impulse response. Then we have the reflections from the surroundings. And we are letting this R of T and N of T as the noise component, so that we have the noisy observation Y of T, which is the desired signal plus the noise. And here the objective is to estimate the desired signal from the noisy observation. So for that we need to have the optimum filter coefficients here. And this is a single channel, or that is, we have the single microphone scenario, and we can have multiple microphones also, that is multiple sensors. So in such case, that observation model, the noisy observation can be written as this, and the corresponding filter parameter matrix is H here, which gives the estimate of the desired signal at a particular sensor, that is sensor 1. So these are the challenges that we observed after going through the literature. So here the one thing that I got in my mind is, can we add these two, that is one is R of T, that is the reflections from the different parts of the room, and the ambient noise. Is it possible to add these two, because they are different? This is the reflections and this is the ambient noise. I have a doubt, can we add these two? So that may be considered as one challenge. Another is how can we obtain the optimal filter coefficients in the case of single microphone, and similarly in the case of multiple sensors or multiple microphones. And after going through these 7 days classes of Professor, we say that these may be the possible solutions for the single channel signal enhancement case and the multi-channel signal enhancement case. So here the model can be that can be implemented with STFT by taking the biorthogonal windows, and another possibility is the joint diagonalization or the generalized eigen decomposition. So these are the references that we gone through to make this presentation. The first one is recently published paper on the D reverberation, and this is the textbook of our professor. And this is also a book edited by our professor. We have gone through actually this paper is not accessible. Just we have gone through the abstract and first page of that paper, which is available. And the remaining part of this paper is not available. We could not able to go through the entire paper of this. So thank you very much. Any suggestions or comments, please? Thank you, sir. Thank you.
Thank you.
Hello.
Good evening, one and all. My name is Tilak Samudrala. Good evening, one and all. My name is Tilak Samudrala, and I am MTech student from NIT Warangal. And my team members are Tasnim ma'am from DRDO scientist, and Nagadevi, MTech student from NIT Warangal. And the topic we are going to discuss today is the constant beamwidth beamformer and robust VAD, the challenges in achieving them, and how we are going to face the challenges. The problem statement is how to achieve constant beamwidth across wide frequency range, and how to address the transient noise in voice activity detection. In the challenges we are going to face in beamforming and VRDR, in beamforming at higher frequencies, we are going to decrease the beam width as at higher frequencies the wavelength decreases, so the beam becomes narrower, so the beam width decreases, and side lobe attenuation will become poor at higher frequencies. And in VAD, the presence of transient noise is a very huge problem, and high computational complexities exist in VAD. And to overcome those challenges, we are going to use FAR filters in beamforming. By using FAR filters, we can get constant beam width as using
Using temporal filtering technique means creating multiple signals with switch. For higher frequencies, beam width is narrower. So to maintain constant beam width, we are using FAR filtering technique. How we can achieve constant beam width means, in single channel, in single microphone noise, we use single weight. Here for wideband signals, it is not acceptable. So that's why we use FAR filters. We are giving different weight coefficients for different frequencies to get constant beam width, constant beam forming. We can achieve this by temporal filtering technique, by creating multiple signals with ensuring some delay between those signals and ensure constant beam width.
And to get the robust voice activity detection, we are going to use the spectral clustering method for separating the speech and non-speech frames. We are going to have different spectral characteristics for speech and noise. By finding those, we are going to separate the speech and non-speech, and we can find our speech signals. And Gaussian mixture models we are going to use by the probability statistics, and we are going to increase the accuracy by this method. Next, the main trade-offs are, even if beam width is going to wider, but the side lobes are also going to be increased as side lobe interference we are getting. And using FAR filters, we are going to ensure robustness, but the computational processing is going to increase. And in voice activity detection, when high sensitivity is getting for speech, sometimes the noise also we are going to compare it as a speech, and we are going to detect it as a speech for noise also. And these are some applications for this topic: speech enhancement systems, surveillance and monitoring systems, and medical diagnosis. Thank you.
good evening all. Yeah, good evening all. This presentation is about the application of array signal processing in underwater acoustic imaging, that is for sonar applications, and some of the challenges. And myself, Sridev from National Institute of Ocean Technology, NIOT Chennai, and co-presenters are Mr. Ajay and Mr. Mahesh, both are from NIT Varangal. Generally, for these sonar systems, there are, if you see, there are different kinds of sonar systems are there, and these different kinds based on the different application scenarios. So one way of classifying different kinds of sonar system is based on the dimension of the image, like 3-dimensional sonar systems or 2-dimensional systems or 1-dimensional systems. So if you take the first case, there is a 3-dimensional imaging sonar. Generally for 3-dimensional or 2-dimensional imaging, it need a planar array of m by n elements, where m is the number of rows and n is the number of columns. But the problem with such kind of planar array is the computational complexity and also the hardware cost. So mainly in almost all the commercial systems available in multi-beam sonars, they won't use a planar array. Instead, they will use a cross array like this, in which this will be the transmitting element, the vertical element will be the transmitting array, and the horizontal one will be the receiving. This will be the transmitting array and this will be the receiving array. So that will have say n number of elements and this will have m number of elements, and this will have a beam pattern in the across track direction, and then by steering that beam to different angles, we can scan in plus y and minus y direction, and at the receiver side again by steering this beam to the minus x and minus plus x and minus minus x and minus plus x, we can get the receiver beams, and wherever these two beams joins, that will give a resolution cell that corresponds to an image. So this is a well established technique in almost all the multi-beam sonar systems. Where this one, that phase will be giving different phase shifts to each element. That depends on the number of elements and the inter-element spacing and what is the frequency we need. Now, one of the problem with the previous system is, say for example, the problem is actually compared to the radar systems, in water sound travels very slowly, like only 1500 meter per second. So if we want to scan the transmitter side, assume that we have to get an image from a 50-meter range. So to and fro distance is 100 meter, and assume that we have 50 such beams to be generated, then the time for each collecting that much data will be around some 3.5 to 4 seconds. So we won't be able to use real-time processing in that. So to achieve that kind of real-time processing, there are different kinds of techniques. One particular technique proposed by a team is divide this transmitting sector beams into different sectors, and in each sector, for each direction, transmit one single frequency. Say for example, beta 1, this direction transmit F1, next direction F2. So each beam width will be tau. So like that cover it. So what happens is, we don't need to wait for all the beams to come back. We can sequentially drive as per this timing, and we can cover this much area very immediately. We don't need to wait. So the advantage is the m number of beams in the previous case has come down to k number of beams. So that is the advantage. So we can drastically reduce, say for example, at least 10 times we can reduce, depends on the number of sectors we select, so that we can do real-time processing. That is the advantage with this. Now, one more problem is, the actual challenge here is, as professor also explained in yesterday's and today's lectures, as the frequency increases, the beam width become narrow and the resolution will be better. But this is better for to image an object above the seabed. Suppose something is there below the seabed, then the frequency should be lower. Means the signal has to penetrate. But the problem is when the frequency become lower, the beam width will be higher and the resolution will be poor. So how to address this problem? Say for example, suppose we want to image something below the seabed, at the same time keep the resolution higher. So what to do? That is the biggest challenge. So this is, how to address this is, still many people have not come up with a solution, such as standard system also doesn't exist. So that is the biggest challenge, some solution to be found out. Probably we can use some kind of sub-array kind of techniques for two frequencies, maybe high frequency for high resolution imaging and a sub-array with low frequencies for signal penetration with probably with some less frequency or something like that. That is one challenge. And another, so this is a typical 3D image. It is from an orbit sonar actually, but this is for the objects above the water. Something is if below water, then how to address this? That is a challenge. Second kind of sonar is two-dimensional imaging sonar. This is actually compared to the first case, it's very simple. There is a linear array which will have a fixed beam width at the broad side, and this will be the azimuth beam width. It will be very narrow compared to the vertical beam width, because vertically the transducer dimension is small. So here for each strip we can generate, and this is well established technique. But here again, as the range increases, the beam width increases. So how to maintain high resolution imaging at higher lengths? So that is the higher ranges. That is the challenge. So for example, this is a very preliminary image from of a shipwreck. Here you can see the curvature. This shows the shipwreck. We are here some internal chambers here, but the resolution is not very high. There are methods to increase this, that is called synthetic aperture processing. There what people have done is they have extended this array virtually, like physically only this array will be there, but by movement of this we can make a virtual array of higher length. So as the array length increases, the resolution will be higher, so we will get high resolution imaging. But there the challenge is how to make the array virtual to maintain that, to ensure that it represents a larger physical array. That is the challenge. Probably people have addressed like AUVs, but still how to make it stable. This is a one-dimensional imaging sonar. Here there is, the sonar will be looking down, and here due to the low frequency, signal will penetrate and go below the seabed. This is the seabed, this is the water column, and this is below the seabed. So why we are getting the penetration here is due to the low frequency. Now coming back to the actual challenge, the first problem, how to combine this low frequency with the first problem, that is that three-dimensional imaging sonar, so that we will get vertical profile, signal will penetrate, at the same time we will get a 2D or 3D image. So that is the challenge to be addressed. Thank you. It is related to frequency, sir. If frequency is lower, signal will penetrate. Say generally if frequency is between some 5 kilohertz to 15 kilohertz, we will get penetration. But for high resolution, we have to go for 100 kilohertz or 400 kilohertz or 500 kilohertz like that. So there is something we have to compromise. If we need penetration, we have to go for low frequency. If we need high resolution, we have to go for high frequency. Otherwise, some sub-array or something to be arrived. Thank you.
Good evening, one and all. I am Manisha from NSTL Vishakhapatnam. I work in the domain of electronic submarine warfare. In that, we work in electronic countermeasure techniques. In that, one of the technique is decoy. Decoy is nothing but the imitation of a submarine. When the enemy releases a torpedo, then we have to move quickly. But the speed of the torpedo is less compared to the speed of the submarine is less compared to the speed of the torpedo. So it is not possible to move as quick as possible. So in order to protect ourselves, we release an electronic unit which just imitates our submarine. So in that submarine, in that electronic unit, basically we generate a signal which is in two modes. Generally we generate in two modes, which is simply noise in one mode, and another mode is echo generation. In echo generation, we receive a signal. With the help of the reception, we'll generate echo. In that echo generation, we need signal enhancement in order to decrease the probability of false detection. So in this, first we do pulse detection. Pulse detection is done using correlation method and then thresholding. And then after pulse detection, we use signal enhancement. In this, I used frequency domain single channel signal enhancement. Basically, we use a single transducer, a single hydrophone. So it is a single channel signal enhancement, and then remaining echo synthesis is done after improving the SNR. So basically, what we use is basically the signal which we receive contains both signal and noise. So we'll transform into the Fourier domain. We'll do FFT, and then we'll get the power spectrum, and we estimate the power spectrum of the noise when the signal is absent. So basically, noise is we assume the noise is generally constant. We know the noise sources, so we'll generate the signal depending upon this expression formulated in step 3, and by making alpha greater than 1, we'll remove all the outband noise. But when the signal plus noise is present, we'll still have some noise. So in order to remove that noise, that is the challenge. In order to, if we remove that noise, then the signal will also get distorted, and then again the SNR is decreased. If the SNR is decreased, then it is difficult to process the echo synthesis. So in order to achieve that, this is the signal. PCW signal is pulsed continuous wave signal. In this, I have taken a pulse and have generated the FFT of that pulse, and then after that, after passing through this spectrum subtraction method, I have done the same thing, calculated the FFT. It has clearly shown that out of band noise is decreased, but in band noise is still present, and it is also clearly shown that the signal level in the in band also decreased. Sometimes because of the noise present in the signal, when we receive signal plus noise, if the signal is of less amplitude, then the problem arrives, because then we'll get, then in this expression the SNR of D of K maybe goes to negative by using this method. That is one of the challenges, but we can use some MVDF filter if the signal if you can't allow the signal distortion. Maybe we can use a maximum SNR filter if we allow some signal distortion, but it depends basically on the implementation, practically how to implement on the hardware. So thank you.
Good evening, one and all. I'm Radhika from NSTL, and one more person is there, Swami Naidu. He's doing MTech in this college itself, but he's unable to attend. So I'll be presenting on behalf of him. So my topic is reduction of in-band noise using S-transform. So S-transform, it is a special case of STFT, short-time Fourier transform. Actually, the basic idea is that we are using IR and FIR filters. We are using these filters for reduction of noise out of band. Suppose if our desired band is from some 20 to 22 kilohertz or 30 kilohertz, and if we receive some signal, then to reduce the out of band noise, we are using these kind of filters. But to reduce the noise in our desired band, this algorithm is implemented. So actually, the algorithm implementation is like this. So in the first step, what we are doing is whatever we are receiving the signal, that signal we are multiplying with the window function, preferably a Gaussian window. And then we are dividing the signal into some length. So on each segment, we are computing the FFT. And then on each block, we are, by some thresholding method, we are doing thresholding, and then on each block we are computing the IFFT also. So the thing is, when we are comparing the input SNR and output SNR, there is an SNR improvement which is in the band. So what kind of challenges is that? First thing is that if the input signal is known, like if we take a known signal, suppose if we are taking some LFM signal and we are adding noise to that signal, then we can compute input SNR. But if we practically receive some signal, we cannot compute SNR for that signal because noise and signal both are combined in that signal. So that is a challenge of this topic. Actually, I have implemented this. So if we take some signal and visually if we can identify what is the LFM signal and what is the noise, we can find out what is the input and output SNR and we can compare. But if the signal is also equally high, then it is difficult to find the SNR. Any suggestions, sir? Okay. Yeah. In that case, we can compute the SNR. But if we receive some signal, in that signal already noise and signal are merged. So how can we compute the SNR? Okay. 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 So in real-time applications, then can we use this method? Okay. 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 And if we visually calculate the SNR, like if we know the points from where the signal is there, and noise also if we know, then is that method accurate, sir, to find the SNR? Okay. Yeah. Track the? Okay. 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 Yeah. Thank you.